Hi, I'm going to be talking here about i.i.d. variables. Now, this is only going to interest you if you're taking a course which has any theoretical element to it. So if you're only doing applied stats, if you're at school, you won't need to be watching this video. Now let's, before I say what this acronym i.i.d. stands for, let's see where in stats we see it appearing when we're doing an intro stats course. We see it appearing in the law, what they call the law of large numbers, a very important concept in probability theory. And the other very important concept in probability theory, the central limit theorem. And those two together leads us to this third use, examining at properties of estimators. So this is to do with the estimation problem. Now let's say what i.i.d. stands for. i.i.d. stands for independent, identically distributed. These two to go together. So independent and identically distributed observations. Now, this is the most restrictive assumption on observations, which allows us to prove things, simplifies the proofs. Okay, so basically let's note that these are restrictions on 1. The degree of dependence between random variables. Dependence, right? So here we've got, when it's i.i.d, it's independent, so that's an extreme case. And also we have a restriction on the what we call the heterogeneity, i.e. How these distributions of the random variables differ. So in this case, they don't differ at all. Let's think of an example. Oh, let's not think of an example. Independent, we know what that means. That means the outcome of one observation does not affect the outcome of another observation. Identically distributed, let's just spell out what this means. If x and y are identically distributed, it means, for example, that they both share the same distribution with the same parameter. So say x is distributed with normally with a mean of 2 and a variance of 1, then if y is identically distributed to x, it will also be normally distributed with a mean of 2 and a variance of 1. Consider a random variable w, which is normal with a mean of 0 and a variance of a half. Would that be identically distributed to x? No, because although they're both normal, the parameters for w are different to that of x. That's a point that I recall was never really drummed into me when I was at college. So I'm telling you, identically distributed means that the distributions are the same and the parameters for that distribution are the same. Okay, example of i.i.d. Tossing a coin n number of times. So that would be an i.i.d. process because the outcomes of each toss are independent of the other ones. And identically distributed because the probability of the outcomes, say a head, is the same for any toss, nth toss that you commit. Okay, so this i.i.d. stands for independent identically distributed observations or random variables, and depending on the nature of your data, this could hold. Alright, so I'm going to relax this i.i.d. because there are cases we have random variables that are not i.i.d. So let's look at the other possibilities. Well, we can have independent but not identically distributed. We say it's heterogeneously distributed. Okay, so that's okay, relaxing. i.i.d. then, independent, heterogeneously distributed. So this is where now our observations, they're independent outcomes, but the distributions, they could be different, or they could be the same distributions but with different parameters. So it's basically they're different, they're different to each other. Next, d.i.d. dependent identically distributed. So now the outcomes, they follow the same, they're identically distributed, but the outcome of one could depend on the outcome of the others. And then the final one, you can see I've relaxed everything here. The dependence, I've allowed it to be dependent. The degree of being different, I've allowed it to be heterogeneous. So d.h.d. dependent, heterogeneously distributed. These three things you're likely to see in grad school rather than undergrad. Going back to the start then, we know that in statistics there are restrictions, degrees of restrictions on the variables, degree of independence allowed, degree of heterogeneity allowed, okay, and then we know that this comes into play in two very important concepts in probability theory: law of large numbers, central limit theorem. Now we saw some relaxations of these conditions, and indeed there are various versions of law of large numbers and central limit theorem depending on the nature of your observations. And then taking these two very important concepts, we can go on then to do theoretical stats. That's where you use all the algebra to look at properties of estimators. Okay, that was a short but necessary video, I think, on nature of observations. I'm Phil, I'm Statistics Mentor.